So let's get back to number 4. It looks like this. Something's weird about that one, right? This looks different from all the other ones. How is it different? All right, I've sketched it here, and I think their graph's more elongated than mine, but oh well. All right, so this is our area, and so what's different about it is, like, the top and bottom are the same function, and then over here the top and bottom are the same function. Like, what am I going to do? There's not really a top and bottom function. What there really is a left and right function. So this is going to be our first opportunity to look at dissecting the area in a different way. We've been in the past always doing rectangles that are vertical. You can also put the rectangles horizontal, right? And then so here's your typical AI, A sub I. It's funny because when I learned this many years ago, AI didn't mean what it means today. The width of these things now, so now the width of this, instead of being delta x, the width is delta y. And then the length of it is going to be, if we think of this function as being g, now g depends on y. The independent variable is y, not x. So it's g of y. And this function is f of y. And I've picked the one on the right to be g. So then this length of this rectangle is g of y minus f of y. So what we're doing is called integrating with respect to y. So we're going to integrate with respect to y. And all of the math that you want to do with that works exactly the same way. So we'll go ahead and see how that sets up. So, basically the idea is when I have a shape that's set up with like a left and right bounding function instead of a top and bottom bounding function, I can say that the area is the integral from a to b of g of y minus f of y dy. All right, so some important differences. A and b are not x coordinates anymore. The limits of integration are y coordinates. So those are the y coordinates of the intersection. All right, and I have dy here, and what else is different? So instead of doing top function minus bottom function, I'm going to do right function minus left function, because the right will be the higher x value. I do a higher x value minus a lower x value, I get a positive area, which is what I want. All right, so that's sort of the general idea, even though I made a bit of a mess here. That says g of y. All right, so what are we going to do for this one? So first, the book makes it pretty clear that the intersection points are 0 and 1, but that might not always be clear or obvious, so we do need to calculate the intercept points, and really the intersection y coordinates is what we really want. So we want to know when 2y squared minus 2y is equal to 12y squared minus 12y cubed. Fortunately, you're very good at solving polynomial equations, so you know you're going to put 0 on one side or the other. It doesn't matter which side. You're going to have 12y cubed minus 10y squared plus 2y, right? Plus 2y. Yeah, I wrote this differently in my notes, but I guess we can still figure it out. I'm going to have, no, because it's 12 minus 2, so it's actually going to be plus 10y squared. All right, and I have negative 12y cubed. That's why I didn't do it this way. And then I'm going to have plus 2y. Yeah, okay. Well, I don't like all those negatives. I really should have, brought the y cubed over here. It would be easier. And then I would have 12y cubed minus 10y squared minus 2y equals 0. It's just formally easier to deal with. All right, so now I'm going to factor out 2y, right? Let's factor out 2y, and then I'm going to have 6y squared minus 5y minus 1 equals 0. So I have y equals 0 as one of my solutions. And then I also have, I can factor this bit as 6y plus 1 times y minus 1 equals 0. Okay, this one's going to give me a negative y coordinate, which is not part of my figure. So I'm going to ignore that, and I'm just going to go with y equals 0 and y equals 1. And that's what I suspected from the drawing anyway, but we really need to verify that. Okay, but those are y coordinates, all right? So because we're integrating with respect to y, we're dealing with y coordinates on our limits of the integral. So the integral is 0 to 1. of my function on the right, which is 12y squared minus 12y cubed, minus my function on the left, which is 2y squared minus 2y, and dy. We're going to write there, dy. All right, so now before you attempt to integrate, this is really important, a mistake a lot of people make. Don't try to integrate this until you simplify it. You have like terms you can combine, right? You have a 12y squared and a 2y squared. We can combine them together. I personally have the habit of liking to put the exponents in descending order, but you absolutely do not have to do that. It's just something I like to do. All right, there you go. And then we're going to do our antiderivative. So, pretty soon you can say, all right, I'm going to raise this exponent 1. It's going to be 4. I'm going to divide the 4 into the 12, and I'm going to get 3. So that's going to be negative 3y fourths. And then I'm going to have plus 10y cubed. That one, unfortunately, doesn't reduce, but this one's just going to be y squared. All right, and we're doing that from 0 to 1. We like the 0 because then we can just go we like the 1 as well, because then it's just negative 3 plus 10 thirds plus 1 minus 0. And that area turns out to be 4/3. Amazing. All right, next up, we're going to look at, oh my God, I'm done with that sheet. Next, we're going to look at number 26. So if you want to have a look at page 396, number 26, that's where we're headed next. Maybe see if you can form a strategy before I lay it out here.